Welcome back, ladies and gentlemen. Today we're handling the single degree of freedom system that we've been working with so far a little bit differently. We will be introducing the frequency domain method and the Statespace formulation. These methods are different from what we've covered in the past. In the past, for every different forcing function or excitation, we've had to do very explicit, very unique solutions. Whereas with these methods, we can have one-size-fits-all type solutions. So let's talk about frequency domain. When we talk about frequency domain, usually two methods are brought up. One is Fourier transform, and the second is Laplace transform. Laplace transform, in my opinion, has way less limitations and it's much more powerful, so that's what we're going to focus on. And pretty much Laplace transform, which is spelled out this way, Laplace transform. This is what we're going to do. And Laplace transform is the process of converting time domain functions to another set of functions, and we like to call them frequency domain functions. And the reason why we convert things from time domain to Laplace domain is that Laplace transform makes things much easier. It converts ordinary differential equation, which, as we've found out so far, can be quite challenging to solve, and it converts them to algebraic equations. And algebraic equations are much more straightforward, and it just makes things easier. It makes it much easier to solve ODEs, and that's what we're going to do. I like to do a demonstration of that. If I have a derivative term, with derivatives, I can't really multiply them. They're not really a multiplication type transformation. So if I have some sort of variable going in, I know for a fact I'm going to get the derivative of that variable over time, but this is not really how we do things in the time domain. But in the Laplace domain, or in the frequency domain, this is in fact how we do things. We can have this Laplace variable s, which pretty much stands for derivatives, and it can by simply multiplying any variable with this Laplace variable, we can have the derivative of that variable. So this is something that we're going to discuss, and to begin with, let's introduce Laplace transform. So for a variable in Laplace transform, we describe the transformation process via this L. That's kind of fancy, and the same variable in time domain is expressed in the brackets. So this is how we define the transformation, and the transformation itself is an integral. It's a one-sided integral, and it has exponential st, this s being the Laplace variable, t being the time, and we have a ut and dt. So this is really what the process is. So if I'm thinking about this derivative term that I have up here, let's do an example of that, where we're converting derivatives to Laplace transform via the Laplace transform. So example. So what I have is, my intention is to do a Laplace transform of the derivative of the ut term. So I have du dt, and what I need to do is to effectively plug in my du dt variable in the position of this ut, like we did up here. So I have my one-sided integral e minus sd dut dt, and I close this off with a dt. Okay, so this is one of those integrations where we have to utilize the concept of integration by parts. So we're doing integration And if you recall, anytime we had this kind of an integration or integral, where we have integral u dv, we end up with u v minus integral v du. So I'm gonna use this trick, this integration by parts trick, to solve my problem down here. Okay, so clearly this dt and this dt cancel out, and what I end up with is the following. I have an e minus st ut, and I need to impose the conditions for my integration, for my integral, and then I have a plus s integral infinity 0 e minus st ut dt. And again, effectively what we've done here is to do integration by parts, and that's what we're ending up with. So now what I want to focus on is this first term. So I'll put an equal sign. I want to focus on this first term. When I put the infinity in, pretty much this negative exponential term goes to 0, because negative exponential terms decrease like that. So if I'm thinking about infinity, I am approaching 0. So when I plug in 0 is where this goes to 1, and I end up with minus u0. And then when I'm thinking about my second term here, so I'm thinking about this term here, my s carries on, so I have my s, and then if I look at this integral, it's matching the same integral that I have up here. So I have s us. So this is really the solution for the Laplace transform of a derivative of a function. Now I could do the same thing for the second derivative, and I need to do this because I'm going to demonstrate something in a second. So in this case I have a second derivative, d square u dt squared, and I'm just going to go ahead and jump ahead and write the solution instead of doing the derivation, but you could definitely spend the time and do this derivation on your own. And this is what we're going to end up with. We have a u dot 0. So now what I want to do is, using my findings to handle the equation of motion that we've been dealing with so far. And our equation of motion has been the following. We've had mx dot dot plus cx dot plus kx is equal to some kind of forcing function. So what I could do is to take a Laplace transform of this equation, and using what I already know, I can get the following transform. So I have mass s squared plus cs plus k us okay, and lastly we have ms plus c u0. There it is. And usually we assume that initial conditions are 0. So if I'm saying my initial conditions are all 0, then what I can say is that this term approaches 0 and this term approaches 0. So anytime I have an equation of motion and the initial conditions are 0, I can simply say, I can simply replace my second derivative term with an s squared. I can replace my first derivative term with an s, and I can have a k, and I will have us, and my forcing function will be ps. So now we can introduce the concept of transfer functions. Transfer function. And using what I have up here, I can derive a transfer function from my equation of motion. And I will have US, which is the output, U being displacement, PS being the input. I will get 1 over ms squared plus cs plus k. And what a transfer system really is basically a transformation between the input and the output. So for some input pt, this is my transfer system ts, and my transfer system is my equation of motion, or 1 degree of freedom system, with the c and the k and the mass. My output will be US. Or I could express it in time domain, it doesn't really matter, UT. And I could pretty much do the same thing for ground motion excitations. So you can imagine if I have some ground motion, this is my single degree of freedom system. The ground has an acceleration. This is a typical earthquake engineering problem. We have CK and M. We can write the equation of motion as follows. We have M x dot dot plus x g dot dot, which is the ground motion acceleration, because mass, or the inertial component, is always dependent on the total acceleration, or the absolute acceleration. So the total acceleration that this mass is experiencing is the motion of the mass plus the motion of the ground. So that's what we have. For damping, we are only dependent on relative terms. So that's what we have. And for stiffness, we are also dependent on relative terms. So again, absolute, relative, relative. Let's keep that in mind. I'll move this thing, this acceleration, ground acceleration term, to the right side. So what I'll have is minus m xg. And this is kind of like my new forcing function, pt. So now what I can do is to do a Laplace transform on this equation of motion, and I'll have ms squared plus cs plus k is equal to minus m x gs. The reason why I don't have an s squared here is because I want to keep my input as ground acceleration. If I do this s squared, then my input becomes ground displacement. And usually with earthquakes, we work with input ground accelerations, not displacements. And so my transfer system is going to be something like this. So I can have t is equal to xs. By the way, I forgot my x here. So xs. I think in the previous example I used u, but you can think of u as x, so it doesn't really matter. So I can have x double dot g s, and this is going to equal minus m over m s squared plus cs plus k. And that's my new transfer system. And this time I have an input ground motion, or ground motion acceleration. Okay, so anytime I want to run a simulation, so I want to do simulation, what I can now do is to simply give the computer my transfer system, let the computer know what it looks like, and then I can choose any arbitrary force. It could be a sine, it could be a cosine, anything you can imagine, pt, and then I will get my output, which is xs. or xt. It's not going to really matter. Okay, so we call that transfer function, and we call this method the Laplace transform. So now what I want to introduce is a different method, which is the state space formulation, and that one's really useful too because it has a lot of tremendous amount of applications in simulation and so forth. So we're going to do that now, and stick around because at the end of this lecture we're going to do an example with Simulink and Matlab. So we're doing state space formulation. Okay, so what is state space? State space is a time domain formulation where we take a second order differential equation and convert it to a first order, and that makes things much easier to solve, and we can use a lot of the explicit numerical integration schemes on Matlab or Python or any of these platforms to solve our problems. So if I have this second order differential equation, or my dynamical system, and I let this equal to some forcing function, what I want to do is to do a change of variables. I'm going to introduce a z1, which is going to be equal to my x, my displacement. I'll introduce a z2, which is going to equal to the derivative of my z1, so derivative z1, and this is going to equal to x dot. So now I'm going to take derivatives of z1 and z2. So I have derivative of z1 is equal to z2, and the derivative of z2 is equal to x dot dot. And if I'm thinking about my equation of motion and I'm transforming it such that I have x dot dot on the left side of my equation of motion, what I'll get is minus k. By the way, I forgot something up here. This should be an x. I'm sure you guys got that though. So I have minus k over m. I've got a z1 here. Then I have a minus c over m. I've got a z2 now. Plus pt over m. Alright, I'm going to take this thing that I have here and I'm going to write it in a matrix format. So let's do that. So what I can say is I have z1 dot z2 dot, this is a vector, and this vector is equal to 0, 1, minus k over m, minus c over m, z1, z2. And this thing is going to equal to, or perhaps we're not done yet. We have a 0, 1 over m, pt. Alright, now this thing is going to equal to, we're going to have an equal sign here, y, so we have our output y, and we have 1, 0, z1, z2. So our output is going to be displacement, and if you recall, z1 is equal to x, so by having this 1, 0 matrix here, I can output z1. And then I will have 0, pt. Okay, so what are these matrices? This first matrix up here, we like to call the state matrix, so state matrix. And it's usually referred to by the letter A. So we've got the A matrix, which implies state matrix. I also have a B matrix, which is my input matrix. And this we call C matrix or output matrix. And lastly, the 0 is what we call D matrix or the throughput matrix. And throughput matrix literally implies that whatever the force is, it has direct impact on the output. So it goes right through. So I mentioned that we're converting a second order differential equation to a first. So if you think about this matrix structure that I have, and now I can say z dot is equal to az plus bp, and then I have y is equal to cz plus dp. And once I have formulated my A, B, C, and D matrices, having known my K, C, and M variables, what I can do is go on Matlab and say I have this transfer system, or let's call it S with capital S. I have this state space system, and you can use this function SS for state space, and you can plug in all these values, A, B, C, and D, and close the brackets. So let's do an example now. This is where all the fun is. Example. I think for this example, I will limit things to Matlab and not pull open Simulink. Hopefully we can do other sessions on Simulink. It's a little more complicated. For this example, I have a single degree of freedom system. Again, we always have this lollipop model, and we got X, and we got the force PT. We have mass, and we have K and C as the stiffness and damping parameters. And we're told that the mass is equal to 50, some sort of units. That's arbitrary right now. We have stiffness that is equal to 100, and zeta that is equal to 0.1. So if I want to know what my C value is, I can always do 2m omega n zeta, with omega n equaling k over m. Alright, I'm going to open up Matlab, and we're going to solve this example via the transfer function or Laplace system and the state space formulation. I'm also going to think about two forcing functions that I'm going to introduce, and one of these is going to be a function that is going to be sinusoidal. So it will look kind of like this. And we're going to choose some random amplitude and frequency for this sine input. And the second input that I'm going to think about will be a step input. So I'll have a zero amplitude force until sometime, let's say 2 seconds, and then the value jumps up to some value of let's say P naught, and this amplitude is P naught as well, and this force continues on. This is a typical step function. That's what we're going to have. So we're going to have case 1 and case 2. So now I'm going to pull open Matlab, and you can see what I've done is I've defined my parameters. I have mass, stiffness, zeta, which is my damping coefficient, and I'm obtaining my omega n, which is my natural frequency, and I'm calculating my damping damping coefficient. So what I can do is to introduce this this Laplace variable s via this equation here. So I can have TF and then put s in there, and you can simply write your transfer function system the way I've written it here, and I'm going to call the transfer function system starting with the first letter. I'm going to call it T. I can do the same thing with the state space formulation. So I have the A, B, C, and D matrices, and because it's state space, I'm going to call it system S, and that's how you plug in the parameters and create the system via this SS function. Okay, so we're going to have two forcing functions. I've defined this time variable. I have P1, which is a sine function, and I have P2, which is force, which is a step function. So what I can do is to simulate up to this point and show you what the forces look like. And here it is. This is what the forces look like. The sine function looks kind of like that, goes up and down, and the step function jumps up at roughly between 2 and 3 seconds is what I think it is. Okay, these are sine and step. So what I want to do now is to use this LSIM, or yeah, so that's LSIM function, and plug in my systems, my forces, and my time variables, so my time vector. And I also want to choose what kind of force I want to plug in there. To begin with, we're going to do the sinusoidal force. So let's get rid of that, and let's plot the solution. So what I'm going to have is what I'm going to do is to press compile. And this is the solution of my Statespace system and my transfer function system to sine input. And because my system is damped, I am seeing a reduction in the amplitudes. But I'm noticing a lot of oscillations that have to do with the complementary solution. And that has to do with the choice of parameters k and m and zeta that we've selected. So this is the response to the first forcing function, which was a sine input. Now we're going to do step input. So I want to say P is equal to P2 and run this thing once again. Let's run it again. There it is. We can see that at roughly 2 seconds, the force is introduced to the structural system. We have a jump to this position, which is 1, and we have oscillation around that position until the oscillations die off and we can have the static solution. Okay, I hope you found this lecture useful. Space formulations and transfer function systems are very powerful. I hope you can really master them. We're going to come back to them when we discuss multi-degree of freedom systems. And the reason why they're so powerful is because you can do simulations with them on your computer. And with dynamics, you really have to know how to do simulations. Anytime you're doing earthquake analysis or you're doing finite elements model of an airplane wing, it's the same thing. The physics is always the same. All right, I'll see you next time. Take care.